Welcome to Schrödinger's Chat, the podcast where I explore the real science behind the biggest questions in the universe, as well as some of the quirkier science we encounter every day. I'm Anna, a physics student with a lot of curiosity and a passion for understanding how the world works. From the smallest particles to the largest galaxies, join me as we uncover the mysteries and wonders of the universe and explore how physics shapes the world around us. Hello, welcome back. This episode, we are doing a bit of a thought experiment about the moon. The Earth and the moon are so closely related, both directly in their physical effects on each other, but also indirectly, in the effects they have on evolution on Earth, and culture, and how we measure time. We all know the moon is there, and I think many people know the odd thing about the moon affecting the tides on Earth, but I thought the best way to understand how much of an impact the moon has on Earth would be to consider what would the Earth be like without the moon. Before we get started, a quick reminder to leave a review or a comment if you like this podcast, and check out the podcast Instagram or YouTube, both Schrödinger's Chat podcast. Here I post all sorts. On YouTube, the episodes themselves if you prefer to listen that way, and on Instagram, extra bits relating to the episodes, STEM book recommendations, and other nerdy science things. So if that sounds like something you would enjoy, do go and have a look. There have been several theories over time about how the moon was formed, but we didn't settle on our current accepted theory until the Apollo missions in the 1960s and 70s. Before we explored the moon, there were three main ideas. One was capture theory, which proposed that the moon was captured by Earth's gravity, having started as an asteroid formed somewhere else in the solar system and passing by the Earth. However, the fact that the moon and the Earth have similar ratios of certain chemical isotopes doesn't suggest that the moon came from elsewhere in the solar system. Also, the orbital pattern of the moon doesn't match with the typical patterns for moons that are captured. In proportion to the Earth, our moon is unusually large, and in order for it to start orbiting the Earth, coming from its own independent trajectory, it would have had to lose a lot of energy. Even if this did occur, it would be far more likely for it to go into an eccentric orbit, which does not match the almost circular orbit that we observe the moon to follow. Eccentricity is a measure of how far the shape of an object's orbit differs from a perfect circle. The second theory is the accretion hypothesis. This suggests that the moon formed from the same disk of dust, plasma, and gas that formed the Earth. This material condensed and collapsed together to form the Earth, and the theory suggests the moon, also created from this material, began to orbit the Earth as the Earth had amassed a greater amount of material and developed the stronger gravitational pull out of the two. One of the drawbacks of this theory is that there are some discrepancies in the proportion of particular elements on Earth compared to the moon. For example, the moon has a much smaller iron core for its size compared to Earth, which doesn't add up if they were formed from the same original material. Another issue is that the angular momentum of the system is too high. The accretion theory would point to more of a slow synchronization of the orbiting pattern, which differs from the high angular momentum of the Earth-Moon orbit that actually occurs, and suggests that there was a large transfer of energy to the system, not a gradual balancing of the orbit. The third theory is called the fission theory. This is the idea that the Earth was spinning so fast that some material basically flew off and started to orbit it. Now, whilst the Earth was initially spinning much faster than it is now, modern calculations can disprove this hypothesis. The calculations show that in order for a chunk of material of that size to spontaneously separate from the Earth would have to be spinning so fast that it itself would probably disintegrate, instead of somehow ejecting one stable object. It is also difficult to see how something that was not just made of the same material that Earth formed from, but literally used to be a part of the Earth, could have, on some counts, very different chemical characteristics. Those were the main theories of the past, but what do we think today? With information gained from analysing samples of material from the moon, we have settled on a different idea. This widely accepted theory is called the giant impact hypothesis. This suggests that the moon was formed from the debris when a planet-sized body called Theia, about the size of Mars, collided with the Earth about 4.5 billion years ago, roughly the same time as the solar system's formation. This solves many of the issues we ran into when examining the other theories. The angular momentum now makes sense, as a collision would transfer a lot of energy to the system, accounting for the high angular momentum. And it explains the similarities in chemical composition, like identical ratios of specific isotopes of oxygen, for example. But it also explains why the Earth and Moon are not identical in chemical composition, as the debris forming the Moon would have been both from Theia itself and also the outer layers of the Earth. This solves why there is a lack of metals, and also the high temperatures created in the collision and lasting for a phase after it would have meant that volatile elements were lost when the Moon had formed. In fact, if you go to the NASA website, there's a very interesting article about the formation of the Moon, and they have an awesome video of a computer simulation of how we think the Moon was formed. And actually, at the moment, it's a very exciting time for developing our understanding of the Moon. With the current Artemis missions sending humans back to the Moon, we can expect to gain a lot of new evidence to help us really define the specific formation scenario that occurred. So I'm excited to see what we may discover in the hopefully very near future. So we've seen that the Moon has been around for almost as long as the Earth itself. And instead of considering what if the Moon just vanished tomorrow, what would the Earth be like, I decided it might be fun if we conducted a little thought experiment of what would the Earth be like if that collision with Theia had never happened in the first place. What if Earth had developed without a moon? The most obvious difference, which I think is the main thing people tend to think of when they consider the moon's effect on the Earth, is the tides. Now, a quick crash course on how the tides occur, just so we can understand what's going on. So, the moon's gravitational force clearly affects the Earth. It pulls on the whole Earth, not just the water, but since water is much easier to move than solid rock and land, the water bulges outwards towards the moon. On the far side of the Earth, across the diameter of the Earth if you like, the water is the furthest away from the moon, and the Earth is being pulled by the moon more than the water, creating a second bulge outwards, away from the moon. Across the whole planet, this makes a sort of rugby ball shape, with the bulges of water being the sort of pointy ends of the ball. As the Earth rotates through these bulges of water, the high and low tides are created across the different global coastlines. So without the moon, would there be no tides? Well, not quite, because the sun also has an effect on the tides. However, although the sun is much, much larger than the moon and has a far stronger gravitational force of attraction, it is also much, much further away, and so has less than half the tidal effect on the Earth that the moon has. So without the moon, there would still be tides, but they would be a lot weaker, and it's the knock-on effects this would have on coastline environments that would really start to make a big difference. You only have to watch one David Attenborough Blue Planet documentary to know how dynamic coastal environments are. And really, the main reason for this is all down to the tides. The Earth rotates through those two bulges of water every 24 hours and 50 minutes, which is one lunar day, causing most coastlines to experience 2 high tides and 2 low tides each day. This means organisms living in these intertidal environments are frequently submerged in water and exposed to open air. As the tide goes out to low tide, the beach is exposed, creating rock pools which create entire ecosystems in one small area. Crabs, anemones, starfish, and seaweed all deposited there as the tide retreats. These organisms have all adapted to withstand the changing tides and the forces of the waves constantly moving around them, with specifically evolved features that help them live with the frequently changing salinity, water availability, and temperature. Other ecosystems, such as estuaries and salt marshes, have also specifically developed around the rhythm of the tide. In an estuary, exposed areas at low tide allow birds to come and feed on various invertebrates on the sandy shores that are otherwise protected by the water at high tide. Salt marshes are also areas of extremely high biodiversity, and even act as carbon sinks, but fundamentally they rely on being flooded and drained regularly by the tides to supply the salty water and circulate the nutrients. These environments are so sensitive to the tides that they are greatly threatened by sea level rise caused by climate change. So you can imagine if the tides were significantly reduced due to the absence of the moon, these ecosystems would look very different or possibly not exist at all. Many species also rely on the tidal patterns to reproduce, like turtles laying eggs on the beach for their young to crawl into the ocean, or horseshoe crabs coming to the shore to spawn during spring tides, which are especially high as they occur when the moon, earth, and sun all line up to create an even greater bulging effect. With weaker tides, this would throw off the whole process for so many creatures. This is a quick opportunity, actually, to mention something not related to tides, but related to the moon's effect on breeding for many species. In the light pollution episode I did, episode 11, I mentioned how corals depend on the moonlight for coordinating mating rituals, which is just another way that the moon significantly impacts life on Earth. Without the moon, perhaps coral would behave very differently or perform a different function, or maybe not even exist at all. I think all of this shows how dynamic and intense these intertidal environments are, but also how fragile they are. Change just the strength of the tide, and suddenly all of these zones of rich biodiversity and highly adapted life would struggle to survive. Since the tides have such an effect on coastal ecosystems and the adaptations of the species that live there, another interesting thought is to consider how weak tides may have affected evolution in general. There isn't conclusive evidence for this, but some scientists suggest that the frequent pattern of flooding and draining of tidal pools could have even helped animals transition from sea to land, as the intertidal zones provide a good environment for creatures that exist both submerged in the ocean and exposed on the beach. As I said, it's an idea still in research, and there are conflicting opinions about it, but it's an intriguing thought to consider. I find it quite shocking, personally, to really consider that the moon's vital role in creating tides could even have affected evolution, not just of coastal organisms, but evolution that led to all land animals, and so by extension, us humans. I'm not saying life on land wouldn't exist at all, but it's definitely interesting to consider how different life may be if the evolutionary path was interrupted by this seemingly small hiccup. The next thing I want to talk about is how the moon has influenced Earth's rotation, seasons, and really our concept of time on Earth. The Earth's rotation is influenced by the moon, and I'm going to start with this as it links to the tidal effects we've just been discussing. We've just looked at how the tides form and work, but the moving tides are not limited to just impacting the oceans and coasts, but they actually apply a braking force to the spin of the Earth, which over time has slowed the Earth's rotation. Back when the Earth was first formed, days may have lasted only 5 to 6 hours, and during the age of the dinosaurs, a day was about 23.5 hours. To understand why this is, we have to look in a bit more detail at the tides. We've already established that as the Earth rotates, the tidal bulges rotate through with it. However, the Earth rotates much faster than the moon, so those tidal bulges don't perfectly align with the moon. Instead, they're slightly ahead of it. Since they are this little bit ahead, the moon's gravity pulls back on the bulges of water, which creates a small braking force on the rotation of the Earth. This is an incredibly weak effect though, and so it's only had an impact because it's been continuously present for billions of years. I mean, it's only increased half an hour since the time of the dinosaurs to now. So half an hour has been added onto the day over 66 million years. And even 1.2 billion years ago, when the first multicellular life developed, it was still 23 hours. So that just puts into perspective for you how weak this braking force is. But still, it has had an effect all the same, and got us to where we are today with our 24-hour days. Other things influence Earth's rotation, like the sun and internal processes in the Earth, but the moon has played a significant role, and if the moon had not formed, perhaps our days would be much shorter. This leads on to further questions in our thought experiment. If the days were different lengths, how would our biological rhythms be different, and our concept of time? I mean, even the word month comes fully from words in ancient languages meaning moon, with the period of time originally being based on lunar cycles. And we divide our years into months, so it would be interesting to consider what method of recording and keeping track of time we would be using without the moon. On the subject of how we record and conceptualize cycles of time, let's talk about the seasons, which the moon also happens to influence. This all comes down to the tilt of the Earth. The Earth does not rotate in a perfectly upright position. It rotates around an axis that's tilted about 23.5 degrees, which is how we get our seasons, because this tilt means that as we orbit the Sun, different areas of the world are more or less tilted towards the Sun. This results in hotter seasons when we are tilted towards it, and colder seasons when we are tilted away from it, and the closer to a pole of the Earth you are, the greater this effect, whereas at the equator and tropical regions, seasons are far less pronounced. Now, this overall existence of the seasons themselves is to do with the Sun and the Earth's tilt towards it, but the moon also plays a role. The moon's gravitational force on the Earth helps to stabilise the tilt, keeping it roughly stable around that 23.5 degrees. Without the moon, the tilt might wobble and change drastically over time. The tilt could be much greater or much less, giving rise to very different seasons. If the Earth was much less tilted, the seasons would be much more subtle, and with a much greater tilt, they would be much more extreme. If the Earth lacked stability of its tilt, it could also fluctuate over a very long time between these two extremes, creating potentially unpredictable climate patterns. Now, it's important to note that without the moon, the Earth wouldn't necessarily be completely chaotic and full of crazy weather events, but more that over long periods of time, the climate would perhaps change more dramatically due to these gradual changes in axial tilt. So it's more geological timescales that we'd be seeing these effects over, not dramatic seasons changing over the course of a year. Over a long time though, this could possibly lead to a different evolution of the planet, its climate, its life, and how ecosystems and their processes function. Life would perhaps have evolved differently to deal with more extreme or more unpredictable weather, or maybe it would just have to evolve more often as the climate and seasons changed more frequently over long periods of time. Finally, I want to talk about the relationship between us humans and the moon. We've already considered that maybe evolution would have taken a different path if the moon wasn't there, which leaves the big question: would humans exist? Unfortunately, that's very difficult to answer. The evolution of humans required very specific conditions and a long, complicated sequence of events. There could still very possibly have been complex life on Earth without the moon, but the journey of that evolution would have looked very different probably, and so it's impossible almost for us to know what life would be like in that scenario and if humans or human-adjacent creatures would exist. So for that question, I'm going to hit you with my favourite sciencey answer, which I think is one of the best things about science. A reasonable answer that invites more curiosity can sometimes be the answer: we just don't know. What I want to look at, however, is the cultural impact of the moon. Human tradition is so closely linked to the moon across so many different cultures for as long as we have walked the Earth. Already, I mentioned calendars depending on the moon, but think about all the mythology and folklore and religion that bases deities or stories or power on the moon and its cycles. The phases of the moon have given rise to superstition, attempts to read the future, and rituals or festivals based around particular times or phases of the moon. The moon has also influenced literature, art, and even language, like we saw earlier with much of the language we use to conceptualize time being rooted in words for the moon and lunar cycles. Observation of the moon has also always been important. The moon is the largest, brightest thing that we can see in the night sky, and it follows predictable and measurable cycles that have made it perfect for navigation and recording time. To be honest, there's so much culture related to the moon that I would love to make a whole episode or a series of short videos about how it has influenced human cultures. But for now, even just considering how significant it is enough to see that without the moon, whole cultures, religions, and concepts of time would be wildly different. I'm going to finish with the moon in relation to scientific endeavour. the moon has driven scientific curiosity for centuries, and in terms of space travel, is one of the most significant places of human exploration. The race to land humans on the moon had huge cultural impacts and is one of the most notable events of modern history. After getting humans into space, landing people on the moon was the most sought-after target in spaceflight. I like how the moon inspires and comforts people, but it also calls people to adventure and scientific endeavour. It kind of makes me wonder, if the moon didn't exist and humans did, how would our approach to space exploration be different? Would we be so obsessed with landing on different planets or objects in space? Maybe we would, and Mars would be the symbolic, most desirable destination as the next closest thing to Earth, which is kind of what we see now. Mars is the next big thing to land humans on. Or maybe it wouldn't, and we would be less interested in getting humans to a place, and more interested in observation. The moon is the most obvious thing in our night sky, but if it wasn't there, maybe there would be more curiosity about other stars and galaxies, or just perfecting space technology in other ways. Again, this is all a thought experiment, and in some ways it's impossible to imagine what we would be curious about in a completely different reality. So we don't know, but I think it is fascinating to consider these things. Sometimes I think we might even take the moon for granted a bit, me included actually. I think only in researching this episode did I fully acknowledge, or at least finally truly consider, just how important the moon has been to development of life, climate systems, and culture on Earth. Well, after all that, I hope you'll agree that the moon isn't just a big rock in the night sky that causes the tides, but it influences ecosystems, seasons, the length of days on Earth, how we record time, and plays a major role in so much of our culture, and may even have impacted the development of life itself. The moon has always been, and still is, an object of awe and inspiration. This is especially apparent now. The Artemis II mission earlier this year rekindled so much excitement and passion for space and science and stirred up a lot of new curiosity. As a passionate science nerd, I can't wait to see the Artemis 3 and 4 missions in the coming years and see what new evidence could tell us about the moon, which is arguably Earth's longest and greatest companion. That's all for today. I hope you enjoyed this episode and thanks for listening. If you have, please go and leave a review or a comment, and remember to check out the social media pages if you want to see some extra Schrödinger's chat content. I'll catch you in the next episode, but until then, stay curious and never let your love of the moon wane. Bye!